Okay, so we'll pick up today where we left off on Wednesday with this second solution to the Navier-Stokes equation. We're looking at a situation where we have two parallel plates. So there are two plates like this. They have a gap in between them. And on one side, we have high pressure. And on the other side, we have low pressure. So we can think of it, we have these two parallel plates and we're pushing fluid through them, in between them. Right, and we're using pressure to do that pushing. So both the top plate and the bottom plate are stationary. We're forcing fluid in between, and we're trying to look at what is the fluid in between those plates, like what does it look like? So we went last time through some assumptions, or just kind of thinking through the problem. What would we know about what the fluid flow would look like? What are the important directions and parameters and things like that? Right, things like we can just, by rationalizing our way through this flow, we can say, well, if the flow is going to be like going through the plate, it's not going to be like going up, it's not going to be going sideways, it's going to be going in the direction that we're pushing it. So just kind of rationalizing our way through like that with these different assumptions, that got us to a simplified version of the Navier-Stokes equations, right? We crossed out almost every term, but we had a couple that were left. Okay, that got us this simplified version. We got two boundary conditions because of the no-slip condition, right? Simplified Navier-Stokes, no-slip condition gives us our boundary conditions. What we're going to do now is solve it and see some of the stuff that we can actually begin to describe if we can solve the Navier-Stokes equation. So let's get a solution. So we have 0 equals dp dx plus mu d squared u dy squared. That's our simplified Navier-Stokes equation. This guy here, this is constant in y. It changes in x, pressure changes in x, but it's constant in y. So if we look, okay, I didn't put axes there. So that's the y direction, that's the x direction. If we looked at pressure, like as we go here, pressure there, pressure there, pressure there, pressure there, pressure there, pressure there, those are all the same. But pressure is going to be changing as we go from left to right. Okay, so it's changing in x, but it's not changing in y. So we can treat that dp dx just as a constant, like we would treat any other constant, because it's constant in y. Let's get all the constants to one side to make our integration lives a little bit easier. So that would be d squared u dy squared. We would add dp dx to both sides and then divide by mu. So this will be equal to 1 over mu dp dx. Okay, and I'll put parentheses around dp dx all the time to just, I don't know, maybe that will help us remember, okay, this like quantity is it's just a constant number. Now, if we want to solve for velocity profile, we have to just solve this differential equation. So we have to integrate 2 times. So that would give us du dy equals 1 over mu partial p partial x dy. And if we integrate that, that is 1 over mu dp dx y plus an unknown constant. We're going to then integrate a second time, so bring the dy over to the right-hand side. du equals, this is 1 over mu dp dx y plus c1 dy. So we can split up our differential, then integrate both sides. This would give us u equals, okay, so we have a group of constants times y dy. That's going to be, integral of y is y squared over 2. So this is 1 over mu dp dx. Our constants, y squared over 2. Plus, now it's c1 dy, that's just c1y, plus a new constant of integration, c2. Then we can take these constants and find out what their actual values are from our boundary conditions. So we can use our first boundary condition is that the velocity at the bottom plate is 0. So that's our first boundary condition. U, velocity at 0 is 0. This tells us that, again, we'll just plug in 0 for y and 0 for u. So 0 equals 0 plus 0 plus c2. So this first term, we plug in 0 for y, that's 0. The second term, we plug in 0 for y, also 0. We're left with c2 equals 0. Our second boundary condition was at the top plate. So at the top, at D, the velocity is also equal to 0. This one gets a little bit more interesting because now we have to plug in D everywhere that we had y. So we have 0 equals 1 over mu dp dx d squared over 2 plus c1 d. This tells us that c1 is equal to minus 1 over mu dp dx times d over 2. Now to figure out our final velocity, we just have to smash all of this stuff back together and put c1 back into our initial equation. If we do that, we get u equals, there's our initial equation, 1 over 2 mu dp dx y squared minus 1 over 2 mu dp dx d times y. Just another way, maybe a simpler way to write it for what we're going to do next. We'll like pull a d squared out of both of these terms, and all of the constants are the same. So this is 1 over 2 mu, or sorry, it should be d squared over 2 mu dp dx times y squared over d squared minus y over d. Right, what this is really similar, but actually a little bit different than the equations that we've already given you for, right, like what does the velocity look like? This equation we could take and use that in the top, right, to describe our velocity profile like this. Right, that's u. That's the equation that we just found. Describes the velocity profile everywhere. If we look at a little bit what that looks like, it's the velocity profile is a parabola. So we should see, right, it's obviously going to be fastest at the middle, but it's going to be parabolic. 0 at the edges, fastest at the middle, and it's going to change as y squared. Right, just a normal parabolic function. We should be able to see that in not only like in our mathematical description, but we should be able to see that in real life. So this is a system that's not exactly the same as the one that we're doing, but it's close-ish. It's one that you guys will do for homework yourselves. Right, this is just a circular pipe, a cylindrical pipe. So this is a cylindrical pipe. We have a pump that's just flowing water kind of around in a loop, and we are looking at a clear section of that pipe. And we're going to be looking at somebody injecting a dye into the pipe. So this guy's going to come and inject dye into the pipe, and you can tell, you can visualize from the shape of that dye profile what the shape of the velocity profile is. There's a pretty good one. You see that one like right in the middle, how it's nice. Like if you look at the top of it, it's a nice, pretty clean parabola. And I told you, very exciting videos. But it is cool to see like some of this, we can math our way to descriptions of reality, which I think is always kind of a cool part of engineering, right? If you look, here, we'll jump ahead just a little bit. Okay, so what he's gonna do is just inject a whole bunch of dye in all at once. And what you can see with this is some of that dye goes right up to the walls of the pipe. And what we just said is that the velocity at the walls should be 0. The velocity of the walls at 0. The dye gets stuck right there at the walls. Okay, so despite the fact that fluid's flowing down through that pipe continually, the dye that's right at the surface of the wall is not moving because of the no slip condition, so it looks like it's just stuck in there on the walls of the pipe. Okay. So again, just to show you, these mathematical descriptions are connected to what's physically happening in the real world. Say we wanted, you probably ran out of space on that sheet, so if you did and you need a new sheet, grab a new paper. What we did is calculate the velocity profile. What we can do from that, though, is calculate other things that we might want to know about the fluid. So if we wanted to know, say, what's the maximum velocity? What's the flow rate? We can use this equation that we just derived to figure out what those things are. So find U max. That's going to be at d over 2 at the center. This is at the channel center. Okay, so if we want to evaluate U, at at the center position at d over 2, that's going to be equal to d squared over 2 mu d pressure dx, all of our constants. And then we're going to plug in d over 2 everywhere that we see y. So this is d over 2 squared divided by d squared minus d over 2 divided by d. And if we look at what that is, this is d squared over 2 mu dp dx. So that first term, that's going to be, we'll have a d squared over d squared. So the d squared parts will cancel out. And at the top, we have a 1 over 2 squared. So this is 1/4 minus, similar kind of thing. We have a d squared over 2 over d. So the d's will cancel each other out, and we're left with just the 1/2 minus 1/2. Okay, if we want to, 1/4 minus 1/2 is -1/4. So this is d squared over, now instead of a 2, it's over 8 mu minus dp dx. So that's our max velocity. I put the minus on the dp dx because that means right, the flow is high pressure to low pressure. It's opposite the pressure gradient. dp dx is from low to high increases, so we go from high pressure to low pressure. So we go opposite of the pressure gradient. But this tells us now specifically, if we think about it, right, this tells us how maximum velocity scales as we scale the channel diameter. As we scale that dimension, it goes as the square of that dimension. It tells us that the max velocity is the inverse of viscosity. So it tells us how viscosity plays a role. If we halve the viscosity, we double the velocity. But if we double the channel width, we quadruple the velocity. And it tells us how it scales with pressure difference, the pressure between one side and the other. It scales, again, directly proportional to that. So we can get a lot of information about what are the important parameters and how much they matter. We could do the same thing with flow rate. So if we wanted to find Q, that would be the same process that we used on the 4th problem of the exam. So if we wanted to find Q, that's the integral over our control surface of V dot dA, which in our Cartesian coordinates, this is equal to the integral from 0 to d, from the bottom of the channel to the top of u. And then our differential area is L dy. Where L is the in and out of the page dimension, the z dimension. So we can find Q over L, the integral from 0 to d of u, which is 1 over 2 mu dp dx y squared over d squared minus y over d, that's u, times dy. Okay. The stuff at the beginning, the 1 over 2 mu dp dx, those are all constants, so those can all come out. 1 over 2 mu dp dx, integral across the channel, y squared over d squared minus y over d dy. The integral of y squared, right, we'll rewrite this, 1 over 2 mu dp dx. Okay, so rewrite our constants. The integral of y squared is y cubed over 3. So this is y cubed over 3d squared for that first term. The integral of y is y squared over 2 minus y squared over 2d. And we're evaluating this from 0 up to d. So obviously, when we evaluate it at 0, both of those terms are 0. So we just evaluate it at d squared. And this equals q over L. Sorry, I messed up. So this is not the right value for u. Right, so that should have d squared, shouldn't it? D squared. D squared. D squared. So turn your 1 into a d squared. Right, is that right? Yeah. See? Missed it. Okay, so that should be a d squared. Then we get q over L is equal to d squared over 2 mu d pressure dx. That's d cubed over d squared, be d over 3 minus d over 2. Which equals a d cubed now over 2 mu dp dx 1/3 minus 1/2. 1/3 minus 1/2, that's like 2/6 minus 3/6. So it should be 1 over negative 1/6. So that, if we, that's d cubed over 1 over 12 mu minus dp dx. Okay, so if we have solutions to the Navier-Stokes equations, all of these things that we might want to know, we can find exact solutions to them. Likewise, if we didn't have an exact numerical analytical solution to the Navier-Stokes equation, if we did a numerical solution, say with a computer, to the Navier-Stokes equation, we could then get analogous numerical solutions to all of these things, like what's the flow rate and what's the maximum velocity and how do all of these things work. So we don't necessarily need analytical solutions. We could do the same types of things with numerical solutions. So with that, let's just spend a few minutes thinking about, if you grab this sheet from up front. If you didn't grab this sheet, that's fine. Or if you're virtual and you don't have this sheet, not a big deal. We're mainly going to do together part one. So part one of this sheet, just want to describe the problem that we're going to be thinking about. It's super simple. We have a tank with water in it. This water level is going to be dropping as the tank is draining. There's going to be water shooting out of this end here. And what you're going to think about is, again, you don't need to, you kind of can do this without any special math, but all you're going to think about is what's going to happen to the velocity of the water that's shooting out of the end of this little spout, and how is it going to change over time, and what are kind of the basic equations that would be governing that. Okay, the solution, this is a cylindrical pipe, but the solutions are going to be very similar to the problem that we just did, where, okay, the flow rate and the max velocity, those are going to be a function of the pressure at, say, this end of the pipe and this end of the pipe. And anyway, so just kind of basically sketch out in part one what would be happening, what is the flow going to be doing over time. Okay, spend like 3 minutes doing it. Again, I'm not looking for depth here. I'm looking for surface level initial thoughts. Okay, so somebody volunteer your answer. What's going to happen and why?
It's slow down.
I agree, it's going to slow down. So as the level in the tank drops, we should see the velocity. It should shoot out slower, less far. Right? As the level in the tank drops, the pressure on the two sides of the pipe, one is going to be atmospheric pressure, and one is going to be rho GH. Right? So if the tank level, if the tank height drops, it drops the pressure by rho GH. So basically continually as it's dropping, the pressure is changing, rho GH. So we should see a nice, it should be super boring, and it should get slower and slower and slower. Agreed? Okay. So never tell me that I didn't show you super exciting videos. We're going to watch that happen. It's going to be awesome. Okay, so there's a little sputtering at first, but okay, so now it's going. So it looks like it's slowing down a little bit. Very exciting. What's happening? What did it just do? Why did it do that? Okay, so you just told me that it was going to decrease. Watch it again closely. See if you can figure out what's happening. You told me, and you were confident that you guys were right. What just happened? And now it increases. Is everything that I just taught you a lie? This is always the question that you should ask. And the answer is usually partially. So what's happening? Let's look. So look super close. There's a reason that there are black lines behind it. So look super close at the black lines and see if you can notice anything that's happening once the velocity starts speeding up. Do you notice anything?
Up at the top.
Yeah, so I'm going to pause it there. So right now we're moving fast. So we have these kind of two states, and we seem to like start in moving slow and then jump back and forth a little bit, and then we're moving fast. When we're moving fast, let's kind of rationalize our way through what's happening. So as this is happening, okay, there is a pressure pushing on one side and a pressure pushing on the other side. Okay, one side is atmospheric, the other side is rho GH. That's changing constantly, but it's slow, right? The tank's draining, it's a big tank, it's draining pretty slowly. So it's not changing that fast, but it's decreasing. When we're moving fast, what types of things are resisting our flow? Well, like one is viscosity, right? But there's going to be friction forces, which is resisting the flow from like through that pipe. So there are like two states. One where friction is relatively high, that's like our slow velocity. And one where friction is a little bit lower, and that's where all of a sudden we start shooting out faster. And we're like switching between these two. Okay, so when we look at this is the fast state where we're moving faster. Look at the little black lines. You can see through it, right? Right, at least right at the top. You can see through the water. You can see the black lines. If we jump back to the slow state, look at it now. You can't see those lines. Let's watch it again and just watch for that. Like watch those lines right kind of at the outlet, right as it shoots out of that pipe. So we're moving slow, high friction. So every time it kind of spurts out, you can see those lines, can't you? And then we kind of get stuck at this point where all of a sudden now we're clear and we can see through it again. What's happening? James?
Turbulent flow versus laminar flow. Is that?
So these are words we haven't said yet, turbulent and laminar. Have any of you heard those words before? In some contexts. So we'll start to unwrap that in class next time and try to figure out exactly what's happening and why we're switching between two different states. What does that look like? What does that mean for some of the models that we just built that are giving us answers that don't match with things that we're seeing in real life? How do we handle that? And kind of what are some of the consequences of that? So where do we see it? What does it happen? How do we start to kind of build that into how we think about flow? So we'll do that next time. We'll wait and discuss turbulent flow and laminar flow on Monday. Should be fun. So that's it for today. There's going to be a new homework posted that's going to be relatively short. That'll be due next week, Friday. So look for that. You should have enough stuff to be able to do that, although it might help. Monday's class might help with that a little bit as well. But we'll do that on Monday. Everybody have a good weekend.